The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
And I'd like to start by acknowledging my co-author, Gordon Salisbury. He was both my undergraduate and my master's student. He is the primary author on this work and unfortunately was not able to be here to present himself, so I'm filling in for him. We take a look. Organization of the presentation. I'll give you a brief introduction just to exactly what are MF-FRP systems, talk a little bit about the slip tests that we did to develop the bearing slip model that we then used in both an ultimate section analysis and for predicting load deformation response of steel reinforced concrete beams that were then subsequently strengthened with FRP reinforcement. We had a number of beam tests that we had conducted that we were able to use to validate our model, get a sense of its accuracy, and then I'll draw some conclusions for you. So first of all, exactly what do we mean by a MF-FRP, or mechanically fastened fiber reinforced polymer system for strengthening? Typical FRP strengthening systems for concrete involve bonding the FRP to the concrete substrate using epoxy adhesives. While effective, the method requires the concrete surface to be properly prepared. The installation itself takes a substantial amount of time, in part because the epoxy needs time to cure, and special knowledge and skills are required for the actual installation. In addition, externally bonded repairs are susceptible to premature failure by delamination of the FRP. It's been a problem we've wrestled with. Mechanical fastened FRP systems, which do not require bonding, provide an alternate strengthening method. In fact, they were first used by military for rapid strengthening of bridges. The MF-FRP systems consist of pre-cured FRP laminates that are connected to the concrete substrate with concrete screws, nails, or anchor bolts. For successful applications, the chosen FRP laminates, which are typically hybrids of carbon and glass fibers, must have enhanced bearing strength to support the load transfer that takes place through the fasteners. The installation method requires minimal surface preparation, uses conventional hand tools and unskilled labor. MF-FRP systems provide comparable strength increase while avoiding the brittle delamination failure common with the externally bonded systems. Now, when they're properly designed, the MF-FRP remains firmly attached to the concrete substrate through failure, as you see in the picture here, and bearing of the fasteners on the FRP allows for a gradual failure mode, which is rather interesting. Now, the force transfer mechanism results in slippage between the concrete and the FRP at the fasteners, as you see in the bottom picture. And if we neglect the slippage effects, that's going to lead to overestimation of the prediction of the strain in the FRP, because it's not the same as the what I'll call the concrete interface strain at the bottom of the concrete. If we overestimate that strain, then we're going to overpredict the force in the FRP. The incompatibility between the strains affects deformations under loading and must be a consideration if we want to develop accurate models for predicting beam behavior. Now, such models have been developed by others. In particular, I'm thinking of Al-Sayed and Nardone for MF-FRP systems fastened with power-actuated concrete nails and with concrete screws. The objective of our work was to develop a bearing slip model for MF-FRP systems that use concrete expansion anchors, and to incorporate this model into the analysis of load deformation response, ultimate strength, and failure mechanisms in MF-FRP strengthened beams. Now, our bearing slip model was developed from test data that we obtained from a series of slip tests. The FRP material that we used in all slip tests was Safe Strip. That's a pre-cured laminate, carbon and glass fibers developed by Strongwell specifically for MF-FRP applications, which means that it does have the bearing strength necessary to support the load transfer through the anchor bolts. Fasteners we looked at were anchor bolts. We considered anchor bolts from two different manufacturers in both 6.35 and 9.25 millimeter diameters. That's a 1/4 and 3/8 inch anchor bolts, which are typical of the sizes we use in this type of an application, and we did consider varying bolt patterns and spacings. Normal weight concrete, 28-day compressive strengths ranging from 27.5 to 55 megapascals. That's 4 to 8 KSI were used in our tests. Now, the free end slip of the connection versus the applied load was what we were mainly after, and you see some of the results of some of the slip tests here in the load slip curves that I'm showing you. The slip test results showed reasonably linear behavior up to what we're identifying as the Safe Strip's bearing yield stress of 234 megapascal, which would be right around here in the 6.35 millimeter tests. And that was regardless of bolt type, diameter, or connection geometry, concrete strength. Behavior after that bearing yield point, however, was sensitive to the variables I've just mentioned, with fastener type and diameter having the greatest influence on behavior. In the interest of brevity, I am going to concentrate on the model we developed for the 6.35 millimeter Hilti KB3 anchor bolts that we took a look at. And in developing our bearing slip model, we took the representative experimental data curve and modeled it in 3 sections. The first section of the curve was best fitted with the straight line up to our bearing yield point, and the bearing yield strength of the FRP is achieved at a corresponding slippage of about 3 millimeters. That bearing yield strength was 234 megapascals. The best fit to the middle portion of the curve, and here was a power relationship that we determined from a simple regression analysis, and then we assumed the final portion of our curve horizontal. Okay. Once the connection achieves its ultimate bearing strength, which for the 6.35 Hilti KB3 bolts was at 350 megapascals, ultimate bearing strength initially achieved at a free end slip of approximately 10 millimeters. And that, by the way, corresponds to the Safe Strip's clamped bearing strength as reported by Strongwell. The ultimate bearing stress was maintained while slip increased until failure occurred at ultimate slips of approximately 20 to 30 millimeters. Now note that the ultimate bearing strength and slips observed in connection tests with other types of anchor bolts and to a lesser extent with the larger diameter KB3 bolts was less than the 350 megapascal that we achieved with the 6.35 millimeter KB3s. Once we had our bearing slip relationship defined for the connection, our next objective was to combine it with load deformation constitutive equations to predict the behavior of MF-FRP strengthened beams. And a process was developed to determine the nominal moment capacity of the cross-section, assuming that the slippage that occurs between the FRP and the concrete varies linearly along the shear span. See here. Maximum slippage was assumed to be located at the bolt furthest from the center line of the beam. And although we did assume a linear slippage for the purpose of this study, it would be an easy matter to incorporate a different slippage span relationship into the analysis. Now, based on the assumption of the linear variation in slippage over the span of the beam, an ultimate section analysis is developed using an iterative procedure, and the nominal moment capacity in failure mode are calculated for cross-sections. We looked at rectangular compression zones. In the section analysis, we assume that concrete crushing occurs at a strain of 0.003, consistent with 318, and use the equivalent rectangular stress block to approximate stress distribution in concrete sections at failure. This section analysis allows for possible failure modes of concrete crushing both before and after steel yield, for an FRP rupture failure mode, and also for bearing failure in the connectors. Now, the process for the section analysis at failure is displayed in a series of flow charts, and I'll show you a few of those. We started by confirming that the section to be strengthened qualifies as a tension-controlled section, and then a maximum slippage is assumed, and the slip at each of the bolts in the shear span is calculated, assuming that linear variation. And then at this point, we bring in the bearing slip model that we developed for the anchor bolts to determine the force that we have in each bolt. The maximum tensile force in the FRP is then determined to be the lesser of either the summation of the force we're getting at each of the anchor bolts in the shear span, or the ultimate tensile strength of the FRP. And if the latter is the case, then the failure mode will be by FRP rupture. Maximum stress then is in the FRP is calculated, and that's based on the gross area of the FRP. And then we get our FRP strain from Hooke's law. Now, concrete stress-strain relationship has to be assumed to determine the location of the neutral axis. And for cases where the concrete was at or near crushing strain, we used the typical Whitney stress block and based on that, then we're able to locate our neutral axis. And we need to verify the assumption that the steel has yielded from strain linearity. And let me note that if the steel does not yield, and it's possible that it doesn't, then the neutral axis is relocated before we calculate our interface strain, which is what we see on our next slide. So the strain at the interface of the concrete and the FRP is calculated. This is the concrete strain. It's calculated based on linearity of strains. And then the strain differential, okay, the epsilon dot in the next box here. Our strain differential then is the difference between the calculated strain at the concrete FRP interface and the maximum strain in the FRP that was calculated from the maximum FRP tensile force. The strain differential is then used to calculate a revised slip in the connection. And at this point then we compare that revised slip with the maximum slip from the iteration in question. And if we are under our chosen limit of difference, and our chosen limit for this study was 1%, if we're under it, we've converged to a solution. If we are over it, then a new iteration is completed using the revised slip as the assumed maximum slip. Run another iteration. At the point that we've converged, then the analysis proceeds to calculation of the ultimate nominal moment capacity and the section curvature. And the equation shown here for the situation where steel yields prior to concrete crushing. Now, we developed a spreadsheet to complete the iteration process for the section analysis. The analysis method is not constrained by type of fastener, nor by the linear slip assumption that we used in the modeling that we did. The spreadsheet can be easily adapted to incorporate a different bearing slip model or slip pattern. And spreadsheet is also capable of analyzing cases in which failure occurs by FRP rupture, by anchor bolt bearing, or by concrete crushing prior to steel yield. Now, we had 5 7.5-foot long simply supported beams that we tested in 2007 and 2013 that we used to investigate the accuracy of our analytical method. All beam cross-sections were rectangular, either 200 by 150 millimeters for the 2 beams tested in 2007, or 200 by 225 millimeters from the 3 beams we tested in 2013. So we were looking at wide, shallow sections here. Concrete compressive strengths were 40 and 60 megapascals, while the steel ratios for the beams ranged from 0.71 to 1.57%, so very ductile beams. There was significant variation in the number of fasteners in each shear span, with bolt spacings ranging from 75 to 150 millimeters, with bolts in either 2 parallel rows or with a staggered pattern of 1 bolt per row. This slide also shows a comparison of the ultimate loads and failure modes. Note that beam 1 from 2013 was not tested to failure, which is why its predicted strength is slightly larger than the experimental result. In all other cases, the experimental ultimate strength exceeded the values from our prediction model, and all beams did fail by yield, failed after yield of the steel reinforcement, as was predicted by our model. Also note that for beam 4, the last beam on the right-hand side here, our method predicted a bearing failure mode, but the actual failure occurred by crushing of concrete, but that was at a load that was 16.7% greater than the prediction. If you contrast that with beam 3 on the slide, which was very similar but with a different connection pattern and predicted to fail by concrete crushing, that is the failure mode we got there, and the difference in the prediction was only 7%. So contrasting the behaviors of those two beams, we get the sense that the achievement of predicted failure mode affects accuracy of our ultimate strength prediction. We also looked at, these tables again show comparison of experimental strengths to analytical results. Let me note that the two beams from the 2007 tests appeared to have significantly greater experimental strengths than the theoretical prediction would give, but when we took a little closer look at the data, the beams compared comparably to a control beam from 2007 that was not strengthened with FRP. So that control beam also tested much higher than we expected. So we took a look at these beams in the percentage of strengthening that was achieved. And here we see agreement between the analytical model and experimental results much closer, suggesting that the proposed methodology accurately predicts our strengthening effects. We also looked at strain in the concrete in the FRP from strain gauge data, and you see the comparison for beam 1 from 2013 over the range of loads here. And as the graph indicates, the difference between predicted and experimental strain increased as load increased. The theoretical prediction is in the solid line, blue for the concrete, red for the FRP, and the dotted line shows you our strain gauge data as the loads increased. Beams 3 and 4 from those 2013 tests followed a similar trend. Now, the section analysis that was developed to account for slippage effects in predicting ultimate load had to be modified to predict the behavior of the cross-section at loads less than ultimate, as the concrete was not near the crushing strain. We used a concrete stress-strain relationship from Totoshini to develop both the strain relationship and also to develop moment curvature diagrams for the strengthened cross-sections over this entire spectrum of possible values of concrete strain. And then those moment curvature diagrams were then used with the virtual work method to predict the load deflection behavior up to ultimate load. And I'll show you one of those examples here. Theoretical midspan deflections were compared to experimental deflections from the beam tests. And as we see here, the predicted deflections for the beams from the 2007 tests is consistent with the experimental results, particularly at service load levels, but also at ultimate loads, where the difference was approximately 6%. That corresponded to an absolute error of only 1.9 millimeters. Predicted deflections for the beams from 2013 tests were also consistent with experimental results up to the ultimate load. I think we saw maximum discrepancies of 29% at service load levels and 23% at ultimate loads. At small loads, all beams were stiffer than predicted, and we expect that was most likely related to the accuracy with which first crack load was calculated. So what conclusions have we drawn from the work? Well, first of all, that the proposed bearing slip model accurately predicts the ultimate capacity of a section, and further that the ultimate strength is better predicted for beams in which the failure mode is also correctly identified. Predictions of strain and deflection were also quite reasonable, and the accuracy of those predictions was not dependent on correctly identifying the failure mode. As to recommendations for future work, we need to take a closer look at failure modes and the effect on predicted beam response. We would also like to explore post-ultimate load deflection behavior and especially work on adapting the method for use with different slippage span relationships in cases for which distribution and bending moment is different than what we had with our beam tests. The proposed model and methodology uses a bearing-slip relationship that is specific to the chosen fastener type, size, and manufacturer. And in order to predict beam behavior with a different fastener, this then requires a bearing-slip relationship specific to that fastener to be developed and incorporated into the analytical model. So the focus of future research, at least in the very near term, should be on determining the prediction sensitivity to variations in that bearing-slip relationship with an ultimate goal of developing a generic relationship that would yield reasonably accurate predictions across a broader range of fastener sizes and manufacturers types. And I'd like to thank you for your attention, and be happy to try to answer any questions.
Yeah, we have time for one question.
You talk about the ultimate strength, I guess, that you're calculating with these.
Mm-hmm.
But I guess for design, we would want the design strength, which you have fee factors applied to that.
Correct.
And what fee factor would we apply to these?
To a certain extent, it would depend upon the particular failure mode. If failure is going to be by FRP rupture, what would probably be recommended is 0.55.
Okay.
If we look at if failure is going to be by yield of concrete crushing after steel yield, 0.9.
Okay.
Thank you.
Dr.